Welcome everyone to this week's edition of our Cassandra Community Webinar Series. Delighted to have with me today Aaron Morton. Aaron is a Cassandra committer and he is based in New Zealand. He's been having a couple of issues dialing in today, but Aaron, let's just test your audio as we didn't have a chance beforehand.
Hi everyone, how are you today?
Great, we can hear you loudly and clearly. Just before we get started, a couple of housekeeping items. First off, please do not forget that this is one of a series of webinars. So upcoming, we have a couple on data modeling. And then on June 11th and 12th, we have the Bay Area Cassandra Summit. It is the premier Cassandra Summit annually. And Aaron is actually going to be presenting a couple of sessions there. So if you like what you hear today, please make sure to book your tickets. The early bird special is expiring at the end of this month. For attending this webinar today, you get to use the SF Summit 25 discount, and you will get 25% off of the current price. Questions today. Usually on these webinars, we reserve about 10-15 minutes at the end to tackle any questions that you have. Please use the Q&A panel inside of WebEx. Ask your question there, and at the end, I will go through those and I will read them out to Aaron, and we will get through as many as we can. So I will pass the ball to you, Aaron, and without further ado, take us away.
Thanks, Christian. Good morning, good afternoon, everyone. Hopefully now you can see a slide that says Introduction to Apache Cassandra. So as Christian said, my name's Aaron Morton. I'm a committer with Apache Cassandra. I've been using the project for a bit over 3 years now, and I'm a DataStax MVP for Cassandra. As Christian said as well, the summit's coming up this year. Last year we had 1 day. Today this year it's twice as big, 2 days. The discount code is on the screen there again, SF Summit 25. I'll be doing 2 talks. The first will be on Cassandra internals. And this is a talk I did at ApacheCon in February in Portland, where I go through how Cassandra works internally, really a deep dive on the code base. And my second talk is titled In Case of Emergency Break Glass. And in that one, I'm going to go through all of the things that I see as a professional Cassandra consultant, the problems that I solve for people on the user list, and try to distill those down to something that can help you as an operator or a developer of Cassandra. Also, this year, DataStax are starting the DataStax Academy, which is a certification program for Cassandra. And during the summit, you'll be able to get certification for free. After the summit, of course, you'll have to pay for it. So that's another great reason to attend the summit this year. Getting started on what we're going to do today, let's start with a brief overview of Cassandra and how we got to where we are today. We'll look at how it works as a cluster of machines collaborating together, how the nodes do their jobs individually, and then a bit of a look at the data model. As Christian said earlier, there is an upcoming talk on data modeling, which I'm sure will go into a lot more detail than I will today. So briefly, Cassandra was started at Facebook when they were dealing with inbox search. It was open sourced in 2008 and shortly thereafter became an Apache incubator project, came out of incubation and became a top-level Apache project at the beginning of 2010. Since then, of course, we've gone and done great things. It's used by companies such as Netflix and Twitter, and Reddit, Rackspace, Urban Airship, Instagram, you name it. It really is now, I think, the premier mature platform in the NoSQL space. If you're looking to understand where Cassandra came from in terms of technology and the things that inspired it, because everything's built on previous ideas. The big ideas that inspired Cassandra were a paper that came out from Google called Bigtable in 2006, which talked about a log-structured storage engine that Cassandra uses and a column family orientated data model, which Cassandra is inspired from as well. There was also a paper the next year from Amazon about their Dynamo system, which described these terms we often talk about called eventual consistency and strong consistency, and how to manage a cluster of machines and how to use gossip-based protocols for those machines to communicate to each other. These are two great papers if you want to get a deep understanding of the background of Cassandra. Of course, there's always got to be a reason for doing something, and I think there's three main reasons for choosing Cassandra. The first and probably the most newsworthy one is scale. People out there with many tens of terabytes of data running in Cassandra clusters distributed around the globe. I think there's also a story there of scale for people who just have hundreds of gigabytes and don't like the idea of storing hundreds of gigabytes on a single node, because it's sometimes painful to move 100 gigabytes around the data center. And there's also scale ideas around throughput. Netflix, of course, a few years ago did a test where they ran 1 million write operations per second through a cluster. The next story is operations, and this is my favorite point as a consultant. It is incredibly easy to keep Cassandra up 24 hours a day, even when you're doing things like upgrading it, because you can do rolling upgrades across your cluster. You can move running systems from one set of hardware to another, or through to even different networking infrastructures. If you do suffer a failure for some reason, chances are it won't affect any data because we have redundancy built into the system. And even in some cases where you do suffer failures, it might be only for a certain small portion of your data. And lastly, the data model. Not everything fits well into the relational database model, and the relational database model in most implementations is quite static and hard to change in a system that's running 24/7. So the data model is, as I said, we've got the column family orientated data model from Bigtable, which is a schema-free system, and nowadays we have the CQL3, which is a data model that brings back tables and has schema, and is a very flexible and changeable model and works well with things like object relational mappers that like to interrogate the database to get a schema. Now let's talk about how you get a cluster of machines to collaborate together to perform some tasks. Imagine we have a cluster of 4 nodes and we want to store a row. This row has columns, but that's not really important at the moment. It has a key though, which is essentially your primary key, and we use that, and our primary key in this example is foo. And we can store this foo row anywhere in the cluster with a replication factor of 3, meaning that we want to store it on 3 nodes. But the important thing is to understand why we choose nodes 1, 2, and 3, so when it comes time to read it back, we can find that row. In Cassandra, we use an idea called consistent hashing, which allows us to evenly map the keys to nodes. So if we have 4 nodes, we want them to each have roughly 25% of the load. And it also allows us to minimize key movements or row movements when nodes join and leave the cluster. We want those to be online operations. We never want to take our cluster down, and we want them to leave our latency and throughput roughly as they were. Our implementation of that starts with an idea called the partitioner. The default partitioner prior to version 1.2 was called the random partitioner. And all this guy does is he takes your row key, applies a transformation, and in the case of the random partitioner, that's an MD5 hash, and generates a thing we call a token. In 1.2, which is the current version of Cassandra, the default is now called the Murmur3 partitioner. It just uses a different hash algorithm, but the idea is the same. We take our row keys, and in this case, in this example, we have 2 keys that are lexicographically close to each other, foo and FOOP, and we run them through the partitioner, and it generates some tokens, which are now essentially randomly distributed. So you can see now FOOP now orders before foo if we order by token. In my example here, to keep things simple, I'm going from 0 to 99, but rest assured, token space is a very, very large space. It's a 120-bit integer. And we can think about tokens as a number line, but it's easier to think about it as a ring. When we do it like this, we can apply some type of clock arithmetic to our counting here. We can say that after we count 98, 99, the next value is 0. So we have now a continuous space, the token ring, which is easier to break up and arrange, which is what we do. Prior to version 1.2, we assigned each node a token, and that allowed us to break up the token space and evenly distribute it. If we look at node 2 here, we can see it has a token range from 1 to 25, because the token range starts with the first value after the previous token, which was 0, so the first value is 1, and comes around to node 2, and it's inclusive at that end, so the token range is 1 to 25. Now we call this the primary range, and it's not a great term to use, because it implies perhaps that node 2 is somehow the primary or the master replica. It's not. It's just there's no other way to really describe this easily. So rest assured that node 2 does not have any special claim over that token range, other than we can use that token range to find node 2. If we look at node 1, you can see its token range starts at 76 because the previous value was 75. And using that clock arithmetic, as we count around past 99, it's inclusive to token 0. In version 1.2, we introduced an idea called virtual nodes, and it's a little bit more complicated, but has some great advantages. And if you understand that initially each node had one token range, it's not that different. What we do now is we give each node lots of token ranges, by default 256, and then they share those around just the same way as we did with the one token range. The ideas for implementing virtual nodes are that it makes it easier to grow and shrink your cluster in smaller steps, so we can grow by 1 and 2 nodes at a time, and it makes it a lot faster for us to replace failed nodes. So virtual nodes are a thing you can enable in 1.2. They're not a compulsory idea. You can use 1.2 without virtual nodes. We're going back to our model about how we locate our node. Whether it's virtual nodes or not, it's the same idea. We take our row key, in this case foo, we run it through our partitioner, that gives us our token, in this case 90, and we find the token range that contains that token. So, and then we find the node, there's the primary that has that as one of its primary token ranges. So here we've gone from foo to token 90, and we found node 1. That gives us 1 replica, but we said we wanted to store 3, so we need a process to find all the replicas. And that's called the replication strategy. And there's always a simple way of doing things, and so we have a simple strategy which orders the nodes deterministically based on their tokens, and then starts with the first node that we found and just counts around. So we get node 1, 2, 3, that's our replication factor of 3, and we're done. There's always a complicated way to do things, and that's called the network topology strategy. It allows us to run a replication factor per data center. And data center in Cassandra doesn't have to be a bricks and mortar facility. They can be machines in different facilities, or they can be machines in the same facility that are even on the same networking subnet, but we just want to consider them as a different set of machines. So some of the reasons we do that are for a geographic distribution. Sometimes we do it to separate workloads. We could have one data center that's handling a transactional workload that's facing your API or your internet or your website, and we can have another data center that's facing an analytical workload through Hadoop integration that allows your back office team to query that data and pull out some important information without interfering and without compromising what's happening with the transactional load. In a multi-data center setup, it's the same idea. In this example, I've got a replication factor of 3 for the West Coast DC and a replication factor of 2 for the East Coast. Normally you'd run the same, but this is just to illustrate that we can have different replication factors, and the idea is the same. In each DC there's a token ring and node assignments, and we use the same process to find the replicas in both locations. But we have to have some way to understand what is going on there. How do we know that these nodes are in different data centers and even different racks, because we can be aware of the rack that your node is in and make decisions based on that. And we use a piece of technology called the snitch. This is a configuration thing. Of course, there's a simple snitch which places all the nodes into the same data center and the same rack. That's kind of handy to start easily. There's a number of other ones. There's a property file one. There are ones that look at the IP address to decide what's the rack and what's the data center, all the way up to the EC2 snitch. And the idea of the EC2 snitch is that we use the AWS region as the data center in Cassandra, so US West 1 and US East 1. And we use the AWS availability zone, which is really a physical building, as the Cassandra rack. If you're doing this, if you've got your data distributed by region and by availability zone, then you have your data in different physical buildings in different geographical regions, and you have quite a distributed database. And you have zero work to do on the client side and zero knowledge of this on the client side. This is all configuration in Cassandra and deployment, and it doesn't really impact the client at all, other than a few things we'll see later on about deciding how long you want to wait for things to be acknowledged. Of course, we need clients. Someone's got to talk to the database. All nodes in Cassandra are peers. There's no master node, there's no name node, there are no nodes that do tasks that other nodes cannot. So a client can talk to any node in the cluster and ask it to do any job. It doesn't have to understand which nodes store the data. The node that the client talks to is considered the coordinator for that request. And a client can talk to any node, and it can send one request to one coordinator and another request to another. It's just a term that helps us understand who's running the read or the write. So the coordinator goes through the process we've talked about. It uses the partitioner and the replication strategy and the snitch to find the replicas, and then it sends messages to those nodes directly and to all three at once and waits asynchronously for those to return. So we don't have any additional network hops here. Node 4 just sends messages to 1, 2, and 3 and waits for them to return. In a multi-data center setup, it's a little bit different. We have a local coordinator, in this case the Node 4 on the left-hand side. He sends those requests to the local replicas. For remote data centers, for reasons of network efficiency, we only send one message over to the remote data center, and we create what we think of as a remote coordinator, who then forwards that message on to other nodes. Each node that participates in the request responds directly back to the local coordinator, so we don't gather those up together in one place in the remote DC and send them back. They all report directly back, but we save some network overhead here by only crossing the data center connection once. The way that these nodes understand all the other nodes in the cluster and their token ranges and what version of the software they're using and things like that is through a process known as a gossip-based protocol, which works just as you'd imagine. The nodes gossip amongst themselves. They don't broadcast. So each second a node gossips to 1 to 3 other nodes, and they gossip to other nodes. And so information spreads around the cluster just like gossip. When the client talks to the coordinator and asks it to send these messages off to other nodes, we have to have some way of saying, well, don't wait forever. If you don't hear back from one of these nodes, maybe that's okay. The way we do that is by specifying a consistency level, and that comes across from the client with each request. And it tells the coordinator, hey, consider this request to be successful when this many nodes get back to you and say they were successful. And this allows us to have requests that can complete in the face of failure. So if we start a request and then the network fails or something like that, then we're okay. Consistency level is essentially an enum. There's a consistency level of any, which is only available for writes, 1, 2, and 3 as you'd expect. But the main ones we use are quorum, a local quorum, which is a quorum in my local data center, and each quorum, which is a quorum in each data center. Each quorum is only available for writes. And the quorum is a simple idea. You take the replication factor, divide it by 2, and add 1. So the replication factor of 3 has a quorum of 2. Replication factor of 6 has a quorum of 4. And you can see as your replication factor increases, the number of nodes that you can have down and unavailable and still maintain a quorum increases as well. So if we were to do a write with a down node, in this case we know the node is down before we start the request, the client talks to node 4. Node 4 works out that the replicas are 1, 2, and 3, but knows that 3 is unavailable. So we've got 2 nodes available. A quorum of RF in RF3 is 2, so we can continue with the request and send that write. Node 4 stores this thing we call a hinted handoff, where locally it remembers the write and that node 3 missed it. And when node 3 comes back online, it sends the write over to node 3. And that process is throttled and managed, and all the nodes in the cluster do this so that we don't overwhelm node 3 when it comes back, but we get in there and we replay this write. Same idea on the read path. If we're doing a read at quorum and we have 1 node down, we can still do the request. And we saw before node 3 down, he missed that write, so that's fine. Nodes 1 and 2 got the write, so we can read from those and get the last written value. But what about when node 3 comes back online, and now nodes 1 and 2 got that right, but node 3 didn't? And we have to work out who actually missed the write. Did nodes 1 and 2 miss a write and node 3 got it, or was it the other way around? And we do that by using timestamps that are stored with every column value. These things are called timestamps, but there's nothing inherently time about them. They're just 64-bit integers, and by convention, they are microseconds past the epoch. So in our coordinator on node 4, if it does a read and node 3 is back online, and the particular hint hasn't been replayed or something, we might have a situation like this. We want to read the purple monkey dishwasher columns, and we read from nodes 1, 2, and 3, and they all come back with different values. We choose the value that has the highest timestamp. So in the case of the purple column, nodes 1 and 2 have cromulent and timestamp 10, so we use that. Node 3 didn't have a value. On the monkey column, node 3 has a value, but its timestamp is less. It's 5, and the others are 10. And the dishwasher column, node 3 returns Tomako with a timestamp of 15, and 1 and 2 have tomato. The interesting thing here is we're not using a quorum of nodes to vote. We're using a quorum of nodes to say that the request was successful. We're using the timestamp to choose the value. So even though node 3 was the only node to say tomato, it has a higher timestamp, and so that's the value we would return to the client. Now, if this happened inside of your read, we have to do some extra work here. So we're reading the purple column, and on the left-hand side you can see nodes 1 and 2 return cromulent, node 3 returns empty. Node 4 would detect those differences and work out the delta between them. So work out that node 3 has to update its value to say cromulent. It sends that mutation to node 3, and it doesn't wait around, and this is what's happening on the right-hand side, and it returns the result to the client. So in this case, we don't really care that node 3 returned the wrong value. Node 3 can continue to return the wrong value. Imagine that its commit log is full and it's just dropping writes, but it's still returning incorrect values. The cluster as a whole, operating at quorum, will consistently say that purple is cromulent, even though node 3 gives us the wrong value. And that's a great example of having a system like this, having a quorum-based system. What we've just seen there is an idea called strong consistency, and it's defined in that Amazon Dynamo paper. This just says that if the number of nodes involved in a successful write plus the number of nodes involved in a successful read is greater than the replication factor, then readers will always get the last written value. And that's an important thing. That, I think, the idea of eventual consistency also sits in Cassandra, but we can be strongly consistent. We can have readers always getting the last written value. We achieve strong consistency by using the quorum for read and write operations. That's by far the most popular way to use Cassandra and the least surprising way. You can also have all nodes involved in the read and one node involved in the write, or the other way around. This allows you to tune your system a bit. There might be some things that are more important to you, and then reads might be more important than writes, or the other way around.
Hey, Aaron, we seem to have lost audio from you. Go ahead. Okay, please hold on, everyone, while we try and get Aaron's audio back. I will be back in a second. Can you hear me?
Yeah. Hi. Sorry about that.
No problem. You were going full tilt. We lost you 3 minutes ago. So rewind to probably the beginning of your achieving consistency, I would.
Okay, sorry about that, folks. Yeah, so achieving consistency, we've seen the consistency level that's specified on the client requests, and we've seen hinted handoff. We also have a process called read repair, which does extra work on the read path so that we can try to avoid having inconsistencies during a read. And we have a manual process called anti-entropy that is run on the command line, normally as a scheduled task, which repairs consistency on disk. So let's jump down now to the node and see how this works as what is essentially just a fast database. All this stuff we've talked about at the cluster level is managing the cluster, but we just need to take data out of memory, put it on disk, take data off disk, put it in memory. And Cassandra is optimized for writes. Your traditional relational database is optimized for reads. Our write path is simple and a lot like a relational database model. We append to a write-ahead log. That's the first thing we do, and that gives us our durability. And then we update some in-memory structures that has a fancy name called memtable. It's really just a hash of the columns. And when we take your write request and we update the memtable, we use those same timestamp reconciliation processes that we saw before. The neat thing about our memtable is that it's always in memory. We never have to page in anything off disk to do the update, and it's lock-free, so it's very fast. We return back to the client, and then later on, we asynchronously flush this memtable to disk, just like a checkpoint process in a relational database. And we create files that can be tens to hundreds of megabytes in size, depending on what's going on. And we create new files. We don't go and update files. And creating new files means we have one long sequential write process rather than smaller write processes that have to seek around. This works really well on SSD-based storage, where there are times this process called write amplification, which means that writing a small amount of data may involve reading data out and then writing it back. So the data is stored in files that are immutable, and we call them SS tables, which just stands for sorted string table, and it has to do with the internal structure of them. On disk, you'll find several files. The most important ones are the data DB, and the star on this slide is roughly going to be the key space and your column family name and the unique identifier for this SS table and its on-disk version format and things. But we have a data DB, which contains your actual rows and the columns and their values. We have an index DB, which is an index of all the rows in the data DB. So this has the row key and then the offset in the data DB. And the filter component, this thing we call that's known as a Bloom filter, which is a probabilistic structure that we use to detect whether a particular row key definitely does not or may exist in our data DB component. After we've run around for a while and created lots of these immutable files on disk, we end up with a situation like this. We've got our row, foo row, but it's spread out over several SS tables. And so the read process now has to piece this together to come up with a coherent value of what we've got from all these different files. And this is a lot like the read at the cluster level. Your data is distributed, and we had to piece it together. And now on the actual node, your data is distributed, and we have to piece it together. So if we look at the read, we've got 5 SS tables here, and things above the dotted line are in memory and so are faster. Things below the dotted line are disk access. We want to read from SS table 1, and we have to read from all these files to work out where the row is. We go to the Bloom filter first, and that says your row might exist. We look at our index sampling, which is some in-memory samples of the -index.db component, which allow us to skip to a particular point in the dash index DB on disk and find the row we're interested in so we don't have to search the whole thing. Once we've done that, then we go to the index DB at the bottom and we do our read. And if you look at SS table 3, we can see the Bloom filter kicking in and doing its job. We've looked in memory in this fast lookup structure, and we haven't had to look any further. So we haven't gone to disk to find that the row doesn't exist there. If you look at SS table 5, we see the degenerate case, Bloom filter false positive. The Bloom filter said your row may exist here, the index sampling said it may exist, but when we got to look on disk, we couldn't find it. So we've wasted a bit of I/O there. Everyone wants things to go faster, so we have two levels of caching inside Cassandra. We have a key cache, which caches things from our index DB. When we put this into the picture, we can see on SS tables 1 and 2, we go through the Bloom filter, get a hit on the key cache, and we skipped one disk access on the index DB file. To make things go even faster, we have a row cache, which caches the entire row in memory, sits above all the disk access, and you can just hit that and your read will be very, very fast. There are two types of row caches. One is an invalidating cache, so writes invalidate the cache, and the other is a write-through cache, so writes update the cache. There's a cost to be had for running around and creating a new file on disk every time you want to write something, and that is that you have to run compaction. And this is just a fact of life of the sort of log-structured storage engine that Cassandra uses. And compaction is a manual and a continuous process. Cassandra does it all the time when it detects enough files on disk. You can also run it manually if you want to. And all compaction does is it takes our mini SS tables and creates one new SS table with the same truth. We have tables 1, 2, and 4. You can see the new table has all the values that we would use from tables 1, 2, and 4 if we did a read. So this reduces the number of tables, SS tables we have to go to, which reduces the latency on the read path and saves space on disk. And quickly, we'll talk about the data model. As Christian said at the start of this, there's an upcoming webinar on data modeling. I think there's actually 2 in the schedule, so I encourage you to attend those. This is just a brief overview. And Cassandra is good at reading data from a row in the order that it's stored, and the order that it's stored is by column name. So typically, an efficient data model denormalizes the data and uses that storage engine order, which means that you have to think about the queries that you want to run ahead of time. This is different to creating systems with a traditional RDBMS because you don't have the complicated and quite capable query engine that you would have in something like MySQL or SQL Server that would allow you to send any sort of query you wanted to later on because it was something you didn't realize that you had to do earlier. At the moment, and there will be, so not just at the moment, there are 2 API choices. Thrift is the API that we had originally. It's still fully supported. Thrift is an RPC mechanism that was created by Facebook. It's used by the clients that you see, such as by Casa, Astanix, Hector. It uses the raw column family orientated data model, which can be completely schema-free. And we have CQL3, which came out of beta in Cassandra 1.2. This is an SQL-like language, query language and data model that introduces the ideas of tables and it allows updates without doing table locking like you have alter table in the database. It's useful if you've got something like an ORM which wants to interrogate the database to find the schema. And I'll be using CQL3 today because it's easier to explain. In a slide deck like this, one of the downsides of Thrift is that it looks a bit different in each different client. Picasa looks different to Hector, of course, and Hector looks different to Astyanic. So it's a bit harder to explain. My examples today are using the CQL shell, which is in the binary distribution. It's also shipped in the package, if you install by package, called CQL-SH. And we'll be doing a Twitter clone, which is essentially the hello world of the NoSQL land. Thinking about our queries up front, we want to post a tweet to our followers, get a tweet by its ID, list tweets by user, have a user timeline, which includes my tweets and the people I follow tweets, and list followers. We start with a key space, which is really just a namespace container. It's the database. And this is a CQL3 statement to create that. You can see it specifies the replication strategy in there, network topology strategy. I encourage you to use that by default because it's a bit tricky to change later. And we've only got one data center and only one node because it was my laptop. So let's set that to 1. And the next thing we do is build some tables. Now, I call these a sparse collection of well-known ordered columns. By well-known, I mean we've defined the column names up front. If you're using Thrift, you don't have to do that. So our first column is going to be for users. This looks just like a normal database. There's nothing scary here. A username, a password, a real name, and the primary key, which equates to our row key that we talked about earlier. We can insert some values in here. Let's put in Fred. He provides the password and his real name. We can select that back and see a nice little display there. We've got a table. Everything's fine. We put Bob in and say he doesn't specify a real name. We just don't provide that in the insert statement, just like normal SQL. We select this back, and this time I put a where clause on there to say I just want to get Bob back. So I said where username equals Bob, and we come back. So our data model so far is pretty simple. We have a user table, has a username and a primary key. We want tweets, and so we have a tweet ID with a big integer value, the value, the body of the tweet, the username, and the timestamp. Not a terribly complicated table. We can insert one tweet into there and do a select and get that back. Here again, I've used selecting by tweet ID because that's our primary key. Our data model now we've a little bit more expanded. We've got 2 tables. Now we're getting a little bit more complicated. The user tweets table stores all the tweets that I've sent. We have a tweet ID, a username, and we look at the primary key clause. We have username and tweet ID. The first part of the primary key, the username, is considered the partition key. This roughly equates to the row key that we saw in our previous examples. The second part is considered the grouping columns, and these are the things that all the other columns are grouped by that are not part of the primary key. So on each internal storage engine row identified by username, we will have many instances of this entity where they will store the username, the body, and the timestamp, and they will be grouped by and ordered by the tweet ID. So there's still one entity here, a user tweet, which is identified by a primary key, which is the username and the tweet ID. We can do an insert here. We put in one tweet for Fred. We can select that back by username. Or we can select back by username and the tweet ID, because that is the primary key that identifies the entity. If we insert a second row into this tweet, we can see that when we do a select just by Fred, they come back ordered by the tweet ID, tweet 1 and then tweet 2, because that's what the grouping columns do. And I can order those in a descending order by just doing order by. I'm not breaking that thing I said before where we use the storage engine order. We can reverse the order, but it's not efficient to come along and say, get me all the tweets for Fred ordered by the body, because we're not indexing on that. That's not efficient in a relational database, and it won't be efficient in Cassandra. We have a timeline, which are the tweets that I've sent and the tweets that my followers have sent. I'm adding a little bit more complexity here again. The primary key is the username and the tweet ID, like we saw on the user tweets column family. But here I've added clustering order by tweet ID descending, which just says reverse the order of the tweet ID, and we do that because we always want to get the most recent tweets. So if I insert 2 rows using this, and then do a select, you can see that they come back with the most recent tweet ID, the highest number first, and that's what we want. We want to get the most recent 20 tweets from this user. So we looked at our data model now. We've added user tweets and user timeline. And you start to see a pattern here. The username is used in the primary key in most of these tables, and that's a common pattern. We've identified the username is a business entity, and we're storing different collections or columns about them. We have counters in Cassandra. They are distributed counters. They are high performance. They are used at places like Twitter to count impressions and things. And you can define a table here called user metrics with counters. We can use this to track how many tweets a user has sent or their number of followers. You update them with a simple statement like this: update user metrics tweets +1, and now we can count how many tweets a particular user has sent. And again, if you look at our data model, the user metrics has username as primary key. Relationships are a little bit trickier. We need 2 tables to store the reflective relationship of followers and following. And we can insert into following and say Bob is following Fred, and insert into followers and say Fred follows. Fred has a follower called Bob. And of course, we would use these when delivering tweets to write into the user timeline. We can select back and see that that's pretty simple there. And so back to our data model now. Again, username is the primary key. It's used in lots of tables, and this is a common pattern that we have, where now we're breaking the data we have for the user up into different tables. So that's a brief tour of the data model. Just a reminder of the summit in June 11 and 12 in San Francisco, and the 25% off discount code SF Summit 25. And that's the end of my slide deck. I think I'll hand over to Christian now to go through the any questions that people may have.
Thank you very much indeed, Aaron. Fasten your seatbelt because we got loads of questions, and we will try to get through as many as we can in the next 12 minutes. So Ashok asks, why use counters? Hold on. Why use counters versus double or float?
Counters do increments. So you don't have to deal with a read-write modify, a read-modify-write pattern where the client reads the value, modifies it, and writes it back, and has to race against other clients doing the same thing. With a counter, you send the server and say increment this by 1, and that is an atomic operation on the server.
Great, thank you. Jay asks, where is the key cache sitting? Is it on JVM heap or off heap?
The key cache is on heap. The row cache is off heap.
Thank you. Zipping through these, Aaron. I love it. Ion asks,
I apologize if they're a bit short, but we're just trying to get through them.
This may be Ion, not sure. I saw 2 rings on the network topology strategy slide, which seems confusing. Can you explain this strategy again, please?
This is a small abstraction leak out of Cassandra. Nodes can only have, there can only be one node that has a token, has a particular token value. This is an artifact of the initial implementation. So we have to, each node has to have a different token ring, a different token. And we logically consider these as, in each data center, as having its own token ring. So if you had different numbers of nodes in different data centers, the token ring on the east DC would look different to the west DC. Typically, they're the same, though.
Okay, thank you. I will take this one. This is from Joe. Will the slides be posted? The answer is yes. We will make Aaron's slides and a recording of this webinar available, usually within 24 hours, and we will email you when they are available. Okay, next one. In case, Timur asks, in case of a cold start of a Cassandra cluster, how are the caches populated and or primed?
Key and row cache both have options to save them periodically, and they both have options to save save a certain percentage of the hottest rows. So if you have a very large cache, you might be suffering a bit on startup time, but you can say persist this cache, and we don't store the values, we just store the things we need to get the values later, but persist this cache every 10 minutes and persist the 20% hottest rows.
Great. Michael asks, actually, a couple of questions related to Cassandra versus HBase. How do you compare storage usage, and how do you compare performance of Cassandra versus HBase?
I'm not an expert on HBase. What I do know, though, is that we can acknowledge requests very, very quickly, and my understanding of HBase is the use of the HDFS can impinge on that. If you're interested in sort of a comparison, when Facebook used HBase for their recent messaging system that they brought out a year or two ago, they did a write-up of how they made the trade-off between the two systems.
Yes, there are lots of resources out there. And there are some benchmarks comparing performance. Actually, if you go to datastacks.com website, we have materials on there. Maybe in an upcoming webinar, we'll do a deep dive into Cassandra versus HBase. Might be a good topic. Arthur asks, are there good ebooks, preferably free, to learn Cassandra further? I'll take a little bit of this one, Aaron. So planetcassandra.org is the community website that we are putting a lot of free materials out there. There are past webinars, lots of blog posts and articles. The DataStax website has stuff as well. I actually know of 4 books being written right now about Cassandra from O'Reilly and Manning and Pact. So those will be hitting the shelves in the second half of the year. Aaron, any other resources that you know of?
No, I think that, like I say, there's a lot of information on Planet Cassandra. The DataStax website itself has great documentation. There's a very active Apache community. If you go to cassandra.apache.org, you find access to that. And there'll be a lot of great material coming out of the summit, which will all be made available as well.
So Shravan asks, row cache, what are the recommendations on row cache when a wide row is, or when wide rows are involved?
Don't use it, because they just don't get as much bang for your buck as you do with the key cache. Row caches are best used when you know roughly know the size of the row. It would be not a great idea to have a row cache for a table that has rows that are generally in the tens of megabytes.
Okay, great. And oh gosh, got so many more here. Michael asks, any GUI data access tools for Cassandra? Actually, my last company has Toad for cloud databases. That's available from Dell's website. It is a free tool and allows you to use SQL to query Cassandra and other NoSQL databases. Any that you know of there, Aaron?
Not off the top of my head. DataStax Ops Center in the Enterprise Edition, I believe, has a Data Explorer. I'm not sure if that's in the free edition. There, if you go to the wiki on the Cassandra Apache site, you will find a list of tools there, and I believe there are some people who have put some together, their GitHub project, so I'd look on the wiki.
Okay, great. You probably can't do this one justice in less than a minute, but try. Can you explain virtual nodes a bit?
The idea of the virtual node is that rather than one node having one chunk of data, it has lots of small ones, and the benefits of that are that you can grow your cluster from 3 to 4 to 5 nodes, whereas previously it was easier to grow from 3 to 6, because we can break up the data space into a lot of smaller parts. And if you have a large cluster above, say, 3 to 6, above 6 to 9 nodes, when you have to replace a node, the number of nodes involved in rebuilding that node is now a factor of the number of nodes in the cluster, whereas previously it was just a factor of the replication factor.
Okay, great. And Aaron Plutz asks, can the cluster still serve reads and writes while shuffling the vnodes?
Yes, it can. That's an online operation.
Great. Rithirong asks, is it better to have many column names or more row keys?
It's a tricky one. It's better to model things so that your read requests tend to read one row or many rows from a same column family. There is, though, a warning, which is very wide rows, I'm talking in the many tens of megabytes, have poor performance, as you might expect. If you're storing something like time series data, it's always a good idea to partition into different rows based on some logical partition in your data, which might be per month. I'd recommend you do a small test where you just write out a month's worth of data and see how big the row gets. If it gets into the tens of megabytes, then you might want to do some more testing to see what's going to happen 6 months down the track when your system is live.
Thank you. Aaron, I think you're on a world record number of questions answered here, but let's try a couple more. Jeremy, how does the client connect to a node in the cluster? Is a node nominated as a master, or can any be connected to? So I think, coming from a relational world there, difficult to wrap your head around that one.
Yep, so clients can connect to any node in the cluster. In fact, many clients do discovery. So the client may only know about a couple of nodes in the cluster, and then it will go to one of those and ask it for information about the entire ring. Clients then typically rotate and recycle around different nodes. There are some interesting failure scenarios. Just because one node says it can't complete a request, you might go to another node and it works. And that just has to do with the particular node's view of the cluster. Some of the more modern clients, Astyanics, has the ability to try to direct reads and writes to nodes that are replicas. Once you get into larger clusters, again beyond sort of 9 to 12, that starts to become something that gives you some performance benefits. At the smaller sizes, there's just a certain probability that one of the nodes you talk to is a replica. But technically, clients don't care. It's just a database with lots of IP addresses.
Okay, great. We're right at the top of the hour, and we have loads more questions, Aaron. Do you mind staying on? Let's maybe go 2-3 minutes because we lost a bit of audio, if you can.
Yeah, that's fine.
Okay, great. Okay. Asim asks, if the nodes in a cluster are in different geographical areas, would the variations in latency impact write throughput?
Typically, if they're in the same data center, Cassandra data center, so they might be in different AWS availability zones, they have a certain limited amount of latency between those AGs. If you're in a multi-data center setup, if you're using local quorum for write, then you're only waiting on nodes that are in your local data center or your local AWS region, perhaps. If you're using each quorum, then you've introduced cross-DC latency into the situation. If you've got a client like Astyanic that can direct you to certain nodes, then you've reduced some of that latency.
Great. Darren asks, what happens if the coordinator is down?
Then your client will just go and try a different node. There's nothing special about the coordinator, and this is one of these interesting failure modes. Like you went to the database and said, hey, can you do me all right? And the database appeared to not be there, but you go to the next IP address and say, hey, can you do it right? And it works. So clients typically fail over and try different nodes.
Okay, thank you. And what happens to the token generation if the ring is broken in multiple places?
Tokens are identified as specified at startup or when you're doing some sort of maintenance move to increase or decrease the number of nodes. Nodes going down is generally thought of in the code as a transient system, transient problem, and the node will come back up. If a node fails completely, there are certain maintenance tasks you can do to either replace or redistribute that load.
Okay, great. Ivan asks, what's the process like for updating from a pre-1.2 ring to new virtual nodes in a production cluster?
There's a script in the bin distribution called Shuffle. There is some information on the wiki, on the DataStax site, and if you go through the user list, you'll find some discussions on it. Even the author of Shuffle, Eric Evans, who is a great software engineer, says do some testing because this process doesn't run very often, so the edge cases don't get caught. So go out there, do some reading, do some testing. The Shuffle process just moves data around in just the same way we move data around when we do when we add new nodes and we take them away or when we do repair. So there's not a chance of losing data, it's just a chance it might get a bit confused at some point. But do some testing, do some reading.
Great. I'll take the next two just super quick. Rick Bryant, you ask about your data model, and it looks very similar to your relational model. What I would say is please attend the next webinar next Thursday at the same time. We're going to talk about some of these concepts and the concept of thinking differently from a relational model. So that will help you. James Gates asks, is there a timeline for DataStax Enterprise to support 1.2 features? We have a release coming at the end of June, and we are targeting 1.2 in that release. Back to you, Aaron. For the tweet example, were the counters stored in a separate column family using counter column type, or does Cassandra 1.2 allow mixing counters with non-counter values?
I don't believe 1.2 allows mixing columns with counter values. Table has to either be all counters and the row key or not counters. Okay,
we are going to end there. Unfortunately, Aaron, there are loads more questions and more coming, but we are not going to have time to get through those. I would encourage everyone who has questions. We have tons of people monitoring Twitter. You can feel free to tweet at Planet Cassandra. We'll make sure to get someone back to you. Stack Overflow is a fantastic resource. Members of the community really monitor Stack Overflow. And then please attend our future webinars as well. Next week, we have Patrick McFadden. He knows so much about Cassandra that he will be able to address these questions as well. Thank you very much, everyone. We really appreciate your time today. Aaron, thank you. As always, this has been great. And you should know you had some groupies on the chat window here saying, well done, fantastic presentation. So we look forward to having you at the Cassandra Summit and in future webinars. Thank you very much indeed.
Thanks, everyone.